All right, we're at, I don't remember the section. I think it's 34.4, wave under refraction. We did reflection, now we're going to do refraction. And we're going to go back to our study of waves. And if you have an incident pulse traveling on um, a rope in A, it's going from a light rope to a heavy rope. Um, the uh, the the wave, the you if we look at A and B on the left hand side, we're going from uh, a light rope to a heavy rope. You'll end up the wave will be transmitted to the heavy rope, but there'll also be a reflection going back, and the since the velocity is equal to the square root of the tension divided by the mu, the mass density, there'll be a change in velocity uh, when you go from the lighter rope to the heavy rope, and also if you go from a heavy rope to a light rope, again because the velocity of the wave is equal to the square root of the tension divided by the mu, the linear mass density, uh, you'll get the pulse will continue on, but at a different speed. The reflected pulse is not inverted and transmitted. Uh, Pulse moves on to the lighter string. We're not so much worried about the reflected, we're worried about the transmitted, and we're looking at light. So here we have an incident ray coming into a different media. So we're going from air to glass. So we have an incident ray coming in, hits the glass. Because the glass light travels at a different speed in glass as it does in other media, the velocity slows down and you have a refracted ray at a different angle than the uh, incident ray. So you still get the reflection off of a smooth surface. You get the reflection. So you have theta one and theta one prime, the incident ray theta one, the reflected ray theta one prime. Uh, but in the glass, you've got the um, theta 2 is at a different angle, and you have the velocity of light in air is v1, and then you have the velocity in the media is v2. So we what we have here is that uh, the sine theta 2 um, over sine 1, sine theta 1 is equal to v2 over v1. So that those are the angles that we get. The angles are related to the velocity. Now, if beam one is the incoming beam in the figure, which of the four red lines are reflected beams, and which are refracted beams? Well, here you can see one comes in, and oh, there, look, there's two. That's reflected. Now notice three comes over here, and off the bottom of this surface, you have a reflected four. And which ones are refracted? Well, one has a different angle than three because three is refracted, but look at four comes out and it five has a different angle than four because it's refracted. So it's going into some medium. I don't know if it's water or glass. Um, and as it comes out, it's changing media again. So the beams 2 and 4 are reflected, beams 3 and 5 are refracted. Now let's look, all rays and the normal lie in the same plane, and the refracted ray is bent toward the normal because velocity 2 is less than velocity 1. So think about this: if it were the reverse, if you were going into a from glass to air, the the uh, the angle would be greater. As a matter of fact, you can uh, see here the angle um, from 1 to 3 is one angle, and uh, the Uh, angle from 4 to 5 is different. Okay, so the you can see that the incident ray and the reflected ray are the theta 1 and theta 1 prime, but the other is theta 1 and theta 2, and they're given by sine theta is equal to the velocity. Okay, when the light beam moves from air into glass, the light slows down upon entering the glass and its path is bent toward the normal. When the beam moves from glass into air, the light speeds up, and upon entering the air, and its path is bent away from the normal because it speeds up. Okay, now this is one way. I learned a different way of um, we'll discuss that. Uh, if you can imagine a barrel rolling on concrete and it suddenly gets to grass, well, it's going to slow down when it gets to grass, and it's going to turn because as part of it is slowing down when it gets to grass, and it turns. It was explained to me as if you were to imagine uh, a marching uh, soldiers marching in their different ranks. As soon as a soldier goes into like a marsh or sand or something like that, they're going to slow down. So the soldiers are going to turn, and you're going to get the slower velocity in the mud or the marsh. And I thought that was a pretty nice analogy. Um, so there's a mechanical analog of refraction, and here's some indices of refraction. These are solids at 20 degrees C and liquids on the right hand side at 20 degrees C. Cubic zirconia 2.2, diamond 2.4. So the cubic zirconia is actually higher. Fluorite is 1.4, fused quartz 1.45, gallium phosphide 3.5, a pretty high index of refraction. Crown glass is 1.5, flint glass is 1.6, ice is 1.3, polystyrene is 1.49, about 1.5, and sodium chloride is about 1.5. Now, in the liquids, benzene 1.5, carbon disulfide 1.63, carbon tetrachloride 1.46, ethyl alcohol 1.36, glycerin 1.47, and water 1.33. And then there's some gas and carbon dioxide that very, very small. Note that all values are for light having a wavelength of 589 nanometers in a vacuum. I'm not sure what color that is. 700 is red, 400 is kind of a indigo. So 589 is probably like a green, somewhere around there. You can check me on that. Okay, now the index of refraction is defined as the ratio of the speed of light in vacuum divided by the speed of light in the medium. Um, so the n is equal to the speed of light in vacuum divided by the speed of light in the medium. For water, it's 1.33. So the velocity is slower. In other words, the speed of light is like 33% faster in vacuum. Now, remember this n equals c divided by v, because we're going to look at v equals c divided by n. We'll see that later. The um, uh, c is equal to or v, the velocity is equal to c divided by n. We're going to use that relationship later. Okay, Snell's law. As a wave moves between the media, its wavelength changes, but its frequency remains constant. The wavelength changes, but the frequency remains constant. So the velocity of one is equal to the wavelength times the frequency, and the velocity of two is equal to the the new wavelength, wavelength 2, lambda 2 times the frequency. The frequency stays the same. It remains constant. So lambda 1 over lambda 2 is equal to V1 uh, over V2. The and here's where I talked about the V is equal to C over N. C divided by N1 over C divided by N2 gives you N2 divided by N1. So notice the inverse relationship. Lambda 1 over lambda 2 is equal to N2 over N1. The index refraction of the second over the refraction index of refraction for the first. So if you multiply those out on the both extremes, you get lambda 1 N1 equals lambda 2 N2. Okay, and N is equal to lambda divided by lambda N, where lambda N is less than lambda. And N1 sine theta 1 is equal to N2 sine theta 2. Snell's law, okay? Sine theta 2 over sine theta 1 is equal to V2 over V1. V1 over V2, again, that inverse relationship, N2 is equal to the ratio of N2 over N1. So N1 sine theta 1 equals N2 sine theta 2. Now, light passes from a material with index of refraction 1.3 into one with index of refraction 1.2, so a lower index of refraction. So it's faster. Compared to the incident ray, what happens to the refracted ray? It bends toward the normal, it is undeflected, it bends away from the normal. Well, the answer is because it's faster, it bends away from the normal. Okay, let me catch up with my notes because I always forget what these talk about. Okay, sine theta 2 over the ratio of sine theta 2 over sine theta 1 is equal to V2 over V1. This is some this is light waves. For light waves, it's Snell's law of refraction, but there's other applications. Sound waves moving upward from the shore of a lake refract on warmer layers of air above. I'm sorry, let's start over. Sound waves moving upward from the shore of a lake refract in warmer layers of air higher above the lake and travel downward to a listener in a boat, making sounds from the shore louder than expected. Light from the sky approaches a hot roadway at a grazing angle and refracts upward so as to miss the roadway and enter the driver's eye, giving the illusion of a pool of water in a distant roadway. We've all seen that. The illusion where it looks like, boy, the road's wet up there, but you get up there and it's dry. It's just a refraction. Light is sent over a long distance in an optical fiber because of a difference in index of refraction between the fiber and the surrounding material. We'll get to fiber optics later. A magnifying glass forms an enlarged image of a postage stamp due to refraction of light through the lens. Okay, and I think, again, N2 sine theta 1 equals N2 sine theta 2. That's just a manipulation of signs of Snell's law. And prisms, the apex angle phi is the angle between the sides of the prism through which the light enters and leaves. Now, for a uniform light, you have the incident beam. It gets refracted, but as it comes out, it has a different angle, angle delta as it exits. And as with different wavelengths, there'll be different angles of when they exit, and that's how a prism breaks up the color spectrum. Okay, and we stop there. We'll go on to Huygens principle next.